Welcome to the Midnight Lesson. If there are topics worth exploring in future videos, share them in the comments. Suggestions help shape upcoming lessons and documentaries. Tonight's lesson explores one of the most extreme and fascinating predictions of modern physics: black holes, regions of space where gravity becomes so intense that space, time, and matter behave in ways that challenge human intuition. This episode is designed as a deep science-focused exploration. The tone blends documentary storytelling with lecture-style physics explanation. Expect real equations described conceptually, real astrophysics, and grounded scientific theory, explained clearly enough to follow while still remaining technically accurate. Settle in. Let the universe get very strange. Chapter 1. Gravity becomes geometry, the physics that made black holes possible. Long before black holes were observed, photographed, or even seriously accepted, the idea began with a deeper question. What is gravity, really? For most of human history, gravity was treated as a force, something that pulled objects toward each other across empty space. This understanding came largely from Isaac Newton in the late 1600s. Newton described gravity mathematically with remarkable accuracy. His equation explained planetary orbits, falling apples, and the motion of comets. Newton's law of gravitation states, gravity force equal to g times mass 1 times mass 2 divided by distance squared, where g is the gravitational constant. This equation worked extremely well. It still works for most engineering and planetary calculations today, but Newton's model assumed something deeper that later turned out to be incomplete, that space and time were fixed, unchanging stages where physics played out. By the early 1900s, small inconsistencies began appearing. Mercury's orbit did not behave exactly as Newton predicted. Light passing near massive objects bent slightly. These were tiny discrepancies, but physics often advances when tiny discrepancies refuse to disappear. Then came Albert Einstein. In 1915, Einstein introduced the general theory of relativity. Instead of gravity being a force pulling objects together, gravity became something much stranger. Gravity is the bending of space-time itself. Space-time is a four-dimensional structure combining 3 dimensions of space and 1 dimension of time into a single fabric. Massive objects like stars and planets warp this fabric. Objects moving nearby simply follow the curves. A useful analogy is a stretched rubber sheet. Place a heavy ball in the center. The sheet dips. Smaller balls placed nearby roll inward, not because something pulls them, but because the surface itself curves. In reality, space-time curvature is not just a visual dip. It changes how distances measure, how clocks tick, and how light travels. Einstein expressed this relationship with field equations that connect matter and energy to curvature. Matter and energy tell space-time how to curve. Curved space-time tells matter how to move. From these equations came a shocking possibility. If enough mass were compressed into a small enough space, space-time curvature would become so extreme that nothing could escape. Not even light. At the time, even Einstein doubted this outcome physically existed. The math allowed it, but nature seemed too orderly for such an extreme object. Then came Karl Schwarzschild. In 1916, while serving in World War I, Schwarzschild solved Einstein's equations for a perfectly spherical mass. His solution described a boundary around massive objects where escape velocity equals the speed of light. This boundary became known as the event horizon. Escape velocity is the speed required to leave an object's gravitational pull. Earth's escape velocity is about 11.2 kilometers per second. The Sun's is about 617 km per second. But if escape velocity equals light speed, about 300,000 kilometers per second, then nothing can escape. Since nothing moves faster than light, anything crossing that boundary is trapped forever. This was the first mathematical description of a black hole, At first, this idea seemed purely theoretical. The universe was assumed to avoid such extremes. But physics has a consistent pattern. If equations allow something, nature often eventually reveals it. To understand how black holes form, the focus shifts to stars. Stars exist in balance between two forces, gravity pulling inward, pressure from nuclear fusion pushing outward. Fusion occurs when hydrogen nuclei combine into helium, releasing enormous energy. That energy produces outward radiation pressure. As long as fusion continues, the star remains stable, but stars have limited fuel. When fusion stops, gravity wins. For small stars, collapse stops when electrons resist being squeezed closer together. This forms white dwarfs. For larger stars, collapse continues until neutrons resist compression. This forms neutron stars. But for the largest stars, typically more than about 20 times the mass of the Sun, not even neutron pressure can stop collapse. Gravity overwhelms everything. The core collapses inward catastrophically. Outer layers explode outward in a supernova. The remaining core shrinks past the critical radius predicted by Schwarzschild. At that point, an event horizon forms. The object becomes a black hole. One of the most important radii in black hole physics is the Schwarzschild radius, Rs equal to 2gm divided by c squared, where g equal to gravitational constant, m equal to mass, c equal to speed of light. If an object is compressed inside this radius, it becomes a black hole. For Earth, the Schwarzschild radius would be about 9 millimeters. If Earth were compressed into a marble, it would become a black hole. For the Sun, the Schwarzschild radius is about 3 kilometers. This reveals something important. Black holes are not necessarily huge. They are extremely dense. Now comes the truly strange part, time. General relativity predicts that gravity affects time itself. This effect is called gravitational time dilation. Near massive objects, time moves slower compared to distant observers. Near Earth, this effect is tiny. GPS satellites actually correct for it. Their clocks tick slightly faster than clocks on Earth's surface due to weaker gravity. Near a black hole, time dilation becomes extreme. From the perspective of a distant observer, an object falling toward a black hole appears to slow down. Light from the object becomes redder and dimmer. At the event horizon, the object appears frozen in time. But from the perspective of the falling object, time continues normally. The event horizon is crossed without noticing anything special locally. This leads to one of the most mind-bending consequences of relativity. Two observers can experience completely different versions of reality, and both are correct within their reference frames. Another strange consequence is gravitational redshift. As light climbs out of strong gravity, it loses energy. Since light's speed cannot change, its wavelength stretches. It becomes redder. Near black holes, this effect becomes extreme. Light escaping near the event horizon becomes dramatically redshifted. Eventually, beyond the horizon, light cannot escape at all. This is why black holes appear black. Not because they suck light in like cosmic vacuum cleaners, but because their gravity prevents light from leaving. However, black holes are not invisible. Material falling toward a black hole forms an accretion disk, a spinning disk of gas and dust heated to millions of degrees. This disk glows intensely in X-rays and visible light. Some black holes also produce jets, beams of plasma accelerated near light speed and launched thousands of light years into space. These jets are powered by magnetic fields interacting with rotating black holes. The physics is still being studied, but involves energy extraction from rotation itself. This leads to another concept. Rotating black holes described by the Kerr solution to Einstein's equations. Unlike simple Schwarzschild black holes, rotating black holes drag spacetime around with them. This effect is called frame dragging. Inside a region called the ergosphere, spacetime itself moves faster than light relative to distant observers. Objects cannot remain stationary there. They are forced to rotate with the black hole. Energy can theoretically be extracted from this rotation through processes like the Penrose process. This means black holes are not just destructive. They are also some of the most energetic engines in the universe. In recent years, black holes moved from theory to direct observation. In 2015, gravitational waves were detected from two merging black holes. This confirmed Einstein's predictions about spacetime ripples. In 2019, the Event Horizon Telescope captured the first image of a black hole shadowing galaxy M87. In 2022, Sagittarius A star, the black hole at the center of the Milky Way, was imaged. These observations confirmed that black holes are not rare cosmic accidents. They are fundamental components of galaxy evolution. Every large galaxy appears to host a supermassive black hole at its center. These objects can contain millions or billions of solar masses. Some theories suggest they help regulate star formation and shape galaxy structure through energy output and jets. This means black holes are not just endpoints of stellar death. They may be architects of cosmic structure, but the deepest mystery remains inside the event horizon. General relativity predicts collapse continues to a singularity, a point of infinite density and zero volume. However, quantum physics suggests infinities should not physically exist. This conflict between relativity and quantum mechanics is one of the biggest unsolved problems in physics. Black holes sit exactly at that intersection. They are laboratories where gravity, quantum mechanics, thermodynamics, and information theory collide. And at that intersection lies a deeper question. If black holes trap everything, what happens to information? That question will lead into Hawking radiation, black hole evaporation, and one of the biggest debates in modern theoretical physics. But before that, the next chapter will explore something even more counterintuitive, how black holes might not just bend time, but potentially reshape causality itself. Chapter 2, Event Horizons, the one-way boundary of reality. To understand why black holes are described as places where time breaks, the focus must move from gravity alone to causality, the chain of cause and effect that structures reality. The defining feature of a black hole is not the singularity at its center. The defining feature is the event horizon, the boundary beyond which events can never influence the outside universe. The mathematics describing this boundary comes directly from the work of Albert Einstein and later solutions by Carl Schwarzschild. But it was decades later, through the work of physicists like Roger Penrose, that black holes were shown to be physically unavoidable outcomes of gravitational collapse. Penrose demonstrated that once enough mass collapses into a small enough volume, spacetime must form a trapped surface. From that point forward, collapse becomes inevitable. Not even light can reverse direction. This concept reshaped how black holes were understood. They were no longer mathematical curiosities. They were physical consequences of Einstein's equations. The event horizon is not a surface. One of the biggest misconceptions is imagining the event horizon as a solid surface, like the surface of a planet or star. It is not. The event horizon is a mathematical boundary in spacetime. Crossing it does not involve hitting anything. There is no wall, no membrane, no sudden flash of energy. Locally, nothing appears special. However, from the outside universe, everything changes. If a spacecraft approached a black hole, observers far away would see the ship slow down as it nears the horizon. Light from the ship would stretch into redder wavelengths. Signals would take longer to arrive. Eventually, the ship would appear frozen at the edge, fading from view. But inside the spacecraft, time would feel normal. The crew would cross the event horizon without noticing a boundary at all. This is not science fiction. This is a direct prediction of general relativity. Why the horizon is a one-way door. The event horizon represents the point where all possible future paths point inward. In relativity, objects do not simply move through space. They move through space-time along paths called geodesics. Near Earth, geodesics allow movement in any direction. Near a black hole horizon, spacetime is curved so strongly that every forward path leads deeper inward. Escaping would require moving backward in time, which physics does not allow. This is why black holes are not vacuum cleaners pulling everything in. Objects must still fall close enough to cross the horizon, but once crossed, escape becomes impossible. Time near the horizon. Physicists like Stephen Hawking explored how time behaves near black holes. Gravitational time dilation becomes extreme. For an observer far away, clocks near the event horizon appear to slow dramatically. If someone hovered just above the horizon, hours for them might equal years for distant observers. Near supermassive black holes, this effect could become enormous. This is not just theory. Precision clock experiments on Earth confirm time dilation exists, though at much smaller scales. The deeper gravity well means slower time flow relative to distant observers. At the event horizon, outside observers would effectively see time stop. But this is a coordinate effect. For the falling observer, time continues normally. This dual reality is fundamental to relativity. There is no universal clock, frame dragging and rotating black holes. Most real black holes rotate. Rotation adds another layer of complexity. Work by physicists including Kip Thorne helped describe how rotating black holes twist spacetime around them. This effect is called frame dragging. Instead of spacetime just curving inward, it also spirals. Around rotating black holes exists a region called the ergosphere. Inside it, spacetime is dragged so strongly that objects cannot remain still relative to distant space. Everything is forced to rotate. This has strange implications. Energy can theoretically be extracted from this region. Black holes can power enormous astrophysical jets. Observations of quasars and active galactic nuclei showed jets traveling thousands of light-years, powered by black holes at galaxy centers. How black holes are observed today. For decades, black holes were inferred indirectly. Today, multiple technologies allow direct and indirect observation. Space telescopes play a critical role. The NASA operates or partners in many of these missions. The Hubble Space Telescope helped measure stars orbiting invisible massive objects at galactic centers. Those measurements confirmed the presence of supermassive black holes. Later, the James Webb Space Telescope expanded this work using infrared imaging. Webb can see through dust clouds that block visible light, allowing observation of star formation and black hole growth in early galaxies. These observations help answer questions like, how fast did black holes grow in the early universe? Did black holes form first, or did galaxies form first? How do black holes regulate star formation? Webb has already detected extremely early galaxies that appear to host massive black holes much earlier than expected. This challenges current formation models. Evidence from stellar motion. One of the strongest pieces of black hole evidence comes from tracking star orbits. Astronomers like Andrea Ghez tracked stars orbiting the center of the Milky Way for decades. These stars move in tight, fast orbits around an invisible object containing about 4 million times the mass of the Sun. Nothing except a black hole can explain that concentration of mass in such a small volume. These measurements helped confirm the existence of Sagittarius A, the Milky Way's central black hole, gravitational waves and black hole collisions. Another breakthrough came when gravitational waves were directly detected. When two black holes orbit each other, they generate ripples in space-time. These ripples travel outward at light speed. In 2015, detectors measured gravitational waves from two merging black holes. This confirmed predictions made by Einstein nearly a century earlier. Gravitational wave astronomy now allows observation of black holes that emit no light at all. It provides direct measurements of mass, spin, and collision dynamics. Information in the horizon. One of the biggest unsolved problems involves information. Physics generally states that information cannot be destroyed, but black holes appear to erase information about what falls inside. Hawking showed black holes slowly emit radiation, now called Hawking radiation. Over extremely long timescales, black holes could evaporate. If black holes evaporate, what happens to the information they swallowed? This is called the black hole information paradox. Modern theories suggest information may be stored on the event horizon itself, encoded in quantum states. This idea links black holes to holography and quantum gravity. This is still an active research field, the horizon as a cosmic laboratory. Black holes combine multiple physics fields: general relativity, quantum mechanics, thermodynamics, information theory. They are not just endpoints of stellar collapse. They are testing grounds for the deepest laws of reality. Observations from NASA missions, gravitational wave detectors, and telescopes like Hubble and Webb continue refining understanding. Each new measurement helps close the gap between relativity and quantum theory. Chapter 3: Singularities, where physics stops making sense. Black holes are often described as cosmic traps, regions where gravity becomes overwhelming and escape becomes impossible. But the event horizon is not the final mystery. It is only the boundary. The deeper mystery lies at the center. At the center of a classical black hole, according to general relativity, exists something called a singularity. A singularity is not simply a very dense object. It is a point where density becomes infinite, volume becomes zero, and space-time curvature becomes infinite. In physics, infinities are warning signs. They usually mean a theory has reached the edge of where it works. The idea of singularities became unavoidable through the work of physicists like John Wheeler, who helped popularize the term black hole, and later through mathematical proofs developed by Subrahmanyan Chandrasekhar, who studied how stars collapse under gravity. Chandrasekhar discovered that stars above a certain mass cannot support themselves once fusion ends. This limit, now called the Chandrasekhar limit, describes when electron pressure can no longer resist gravity. Beyond this point, collapse continues. And if collapse continues without limit, classical relativity predicts a singularity must form. What does infinite density really mean? Infinite density does not mean a very heavy object packed tightly. It means the mathematics describing spacetime breaks down completely. General relativity describes gravity as curvature in spacetime. But if curvature becomes infinite, the equations stop producing meaningful answers. It becomes like dividing by zero in mathematics. The system stops making physical sense. This creates one of the biggest problems in modern physics. General relativity works extremely well for large objects, stars, galaxies, black holes. Quantum mechanics works extremely well for tiny objects, atoms, particles, radiation. But inside a black hole, both must apply simultaneously, and currently they do not agree. Quantum physics refuses to allow true singularities. Quantum mechanics suggests nature does not allow infinitely small points of matter. Instead, quantum uncertainty means particles cannot be perfectly localized. There is always uncertainty in position and momentum. This means the idea of matter collapsing into a true point might be physically impossible. This conflict between relativity and quantum mechanics is one of the biggest unsolved problems in science. The search for a theory that combines them is called quantum gravity. Planck scales where new physics must appear. Physicists believe new physics must appear at something called the Planck scale. This is defined by three constants: speed of light, gravitational constant, Planck constant. At the Planck length, about 1.6 times 10 to the minus 35 meters, spacetime itself may become grainy or quantized. At these scales, classical geometry may stop existing. Instead of smooth spacetime, reality may behave more like fluctuating quantum foam. Inside black holes, matter may collapse to this quantum limit, not to an infinite singularity. But current instruments cannot test physics at this scale directly. Information cannot be destroyed, or can it? One of the biggest puzzles involving singularities is information. In quantum physics, information must be conserved. If something happens, the full quantum state must remain encoded somewhere in the universe. But if matter falls into a singularity and is destroyed, information will be lost forever. This violates fundamental quantum theory. This paradox became one of the biggest debates in physics during the late 20th century. Physicists including Leonard Susskind argued that information must survive black holes in some form. Later, theoretical work by Juan Maldacena suggested space-time and gravity might emerge from quantum information itself. This idea led to holographic theories of the universe. The holographic principle suggests that information inside a volume of space might actually be encoded on its boundary surface. For black holes, this means everything that falls inside might be stored on the event horizon itself. If true, singularities may not destroy information. Instead, information may be preserved in extremely complex quantum states. This idea is still being tested mathematically and theoretically. Could singularities be something else entirely? Some theories suggest singularities might not exist physically at all. Instead, collapse may stop at ultra-dense exotic states of matter. Possibilities include quantum gravitational cores, Planck density objects, exotic matter stabilized by unknown forces. Some speculative models even suggest black holes could contain new universes or connect to other regions of space-time. There is currently no direct evidence for these ideas, but the mathematics does not fully rule them out. Observational clues from modern astronomy. Modern observatories continue testing black hole physics. Gravitational wave observatories like LIGO Scientific Collaboration detect black hole mergers by measuring distortions in spacetime smaller than a proton. These observations allow precise measurement of black hole masses and spins. So far, observations match general relativity extremely well, but small deviations might eventually appear, revealing quantum gravity effects. Why black holes are so important to physics. Black holes are not just exotic objects. They are essential tools for testing reality's deepest laws. They connect gravity, quantum mechanics, thermodynamics, information theory, cosmology. No other known object forces all these fields to interact simultaneously. This is why black holes are considered laboratories for fundamental physics. Time and causality near singularities. Near a singularity, general relativity predicts time and space may swap roles. Inside the event horizon, moving toward the singularity may be as unavoidable as moving forward in time outside a black hole. This means the singularity may represent not just a place in space, but a point in the future that cannot be avoided. This idea remains deeply theoretical, but emerges naturally from relativity equations. What if singularities don't exist? If quantum gravity removes singularities, black holes may contain extremely dense cores instead of infinite points. These cores could contain compressed matter, exotic particles, or unknown quantum states. Future observations of gravitational waves or black hole collisions may help test these ideas. Small differences in wave patterns might reveal whether singularities exist or are replaced by quantum structures. The quiet reality of the unknown. Despite decades of research, singularities remain beyond direct observation. No instrument can see past an event horizon. Everything known about singularities comes from mathematics, indirect observation, and theoretical models. This uncertainty is not failure, it is the frontier of physics, the calm perspective. From a human perspective, singularities are unimaginably distant and unlikely to affect daily life. But they represent something profound. They mark the boundary of current understanding. They show that even the most successful theories in science are incomplete, and that the universe still holds deep mysteries waiting to be solved. Where Chapter 4 goes next. If Chapter 3 explored where physics breaks down, the next step explores something even stranger. Black holes might not be completely black. The next chapter will explore Hawking radiation, black hole temperature, and how black holes may slowly evaporate over time. Even objects that trap light might not last forever. Chapter 4. Hawking radiation, how black holes slowly fade away. For most of the 20th century, black holes were thought to be simple in one important way. Once something fell inside, it was gone forever. Black holes could grow larger, they could merge, but they could never lose mass. Then in the 1970s, a new idea emerged that changed everything. The idea came from combining two fields that usually do not cooperate well, general relativity and quantum mechanics, and it came largely from the work of Stephen Hawking, building on earlier work from Jacob Bekenstein. Together their work suggested something deeply strange. Black holes are not completely black. They glow very faintly, very slowly, but fundamentally, black holes can lose mass and eventually disappear. The first clue, black holes and temperature. The story begins with thermodynamics. Thermodynamics studies heat, energy, and entropy. Entropy measures disorder, or the number of microscopic ways a system can exist. Bekenstein proposed something radical. Black holes should have entropy. At first, this seemed impossible. Entropy is usually tied to particles moving and exchanging energy. Black holes appeared to have no internal structure visible from outside. But Bekenstein noticed something important. The area of a black hole's event horizon behaves like entropy. If matter falls in, the horizon grows. If two black holes merge, the total horizon area increases. This matched the second law of thermodynamics, which states total entropy must increase over time. Bekenstein proposed that black hole entropy is proportional to the surface area of the event horizon, not the volume. This was strange but mathematically consistent. If black holes have entropy, then they must also have temperature. And if something has temperature, it must emit radiation. At first, this seemed absurd. Nothing escapes a black hole. But quantum physics had something to say about that. Quantum vacuum is not empty. In classical physics, empty space is truly empty. In quantum physics, empty space is alive with activity. Quantum fields constantly fluctuate. Particle pairs briefly appear and disappear everywhere in space. These are called virtual particles. Normally, these pairs annihilate almost instantly. They borrow energy from the vacuum and return it immediately. But near an event horizon, something different can happen. How Hawking radiation works. Imagine a pair of virtual particles forming right at the event horizon. Normally, they would annihilate. But if one particle falls inside the horizon while the other escapes, annihilation cannot occur. The escaping particle becomes real radiation. From an outside observer's perspective, the black hole has emitted energy, but energy cannot appear from nowhere. That energy must come from the black hole's mass. Over extremely long timescales, this radiation causes the black hole to lose mass. This radiation is now called Hawking radiation. It is one of the most profound predictions of modern physics. Black hole temperature. Hawking calculated the temperature of a black hole. The formula shows temperature is inversely proportional to mass. Large black holes are colder. Small black holes are hotter. For example, a black hole with the mass of the Sun would have a temperature far colder than the cosmic microwave background. It would absorb more radiation than it emits. A tiny black hole, much smaller than an asteroid, would be extremely hot and radiate strongly. This leads to a surprising conclusion. Large black holes live a very long time. Small black holes evaporate quickly. Black hole lifetimes. The lifetime of a black hole depends on its mass. A stellar mass black hole could last far longer than the current age of the universe. A supermassive black hole could last trillions upon trillions of years. As black holes shrink, radiation increases. The final stage of evaporation could be explosive, releasing huge energy. No one has observed a black hole evaporating yet. The universe is not old enough, but the math is extremely strong. Thermodynamics and deep physics. Hawking radiation linked three major areas of physics: gravity, quantum mechanics, thermodynamics. This was revolutionary. It suggested gravity is not just geometry. It might have deep connections to information and energy at the quantum level. Many physicists now believe space-time itself may emerge from quantum information. Black holes helped open that possibility. The information paradox gets worse. If black holes evaporate completely, what happens to information about everything that fell in? Quantum physics says information cannot be destroyed, but Hawking radiation, in its simplest form, appears random. It does not seem to contain information about what formed the black hole. This created the black hole information paradox. This paradox is still unresolved. Some theories suggest information escapes slowly in Hawking radiation. Others suggest information remains encoded on the event horizon's surface. Some suggest information is preserved in subtle quantum correlations. No final answer exists yet. Modern observations and space telescopes. Modern telescopes help study environments around black holes, even if Hawking radiation itself is too faint to detect directly. Organizations like NASA operate major observatories that help study black holes. The Hubble Space Telescope helped confirm black holes by measuring star motion near galactic centers. The James Webb Space Telescope is helping study early galaxy formation and early black hole growth. Webb can see through dust clouds using infrared light. This allows observation of the earliest black holes forming in young galaxies. These observations help test models of black hole formation and evolution. Black holes as thermodynamic objects. Black holes follow 4 laws that mirror thermodynamics. The surface gravity relates to temperature. The event horizon area relates to entropy. Mass relates to energy. Black hole mergers increase total horizon area, like entropy increases. This deep connection suggests gravity and thermodynamics may come from deeper underlying physics. Some physicists suspect space-time itself emerges from quantum information networks. Do black holes really evaporate completely? Some theories suggest black holes may leave tiny remnants instead of disappearing completely. Others suggest evaporation is complete and information is released gradually. Future theories of quantum gravity may answer this. Observations of tiny primordial black holes, if they exist, might provide clues. Some theories predict small black holes formed right after the Big Bang. If any remain, they might be evaporating now. No confirmed detection exists yet. The final stages of evaporation. As black holes shrink, temperature rises. Eventually, radiation output increases rapidly. The final stage might release energy comparable to nuclear explosions or more. This would be extremely brief and extremely powerful. No confirmed observation exists, but detectors search for possible signals. Why Hawking radiation matters. Hawking radiation showed black holes are not just gravitational objects. They are quantum objects. They follow thermodynamic rules. They connect fundamental forces. They challenge assumptions about information, reality, and spacetime itself. Black holes became central to attempts to unify physics, the long, slow future of the universe. In the far future, stars will stop forming. Galaxies will fade. Black holes may dominate the universe. Then, over unimaginable time, black holes may slowly evaporate. Eventually, only radiation may remain. This is one possible prediction of current cosmology, a quiet perspective for sleep. Black holes exist across the universe. They shape galaxies. They bend time. They slowly radiate energy across trillions of years, but they are distant, silent, patient. The universe operates on timescales so vast they are almost peaceful. Black holes do not rush. They change slowly across cosmic time. Where Chapter 5 goes next. If Chapter 4 explored how black holes can slowly disappear, the next step explores something even stranger. What happens to space and time inside rotating black holes? The next chapter will explore Kerr black holes, inner horizons, and whether time and space can swap roles deep inside. Chapter 5. Rotating black holes, when space-time begins to twist. Most black holes in the universe are not motionless, perfectly symmetrical objects. Real astrophysical black holes are almost always rotating, because the stars that formed them were rotating, and the matter that feeds them from surrounding space also carries angular momentum. Once a black hole forms, that rotation does not simply disappear. Instead, it becomes locked into the structure of space-time itself. The mathematical description of rotating black holes comes from the Kerr solution to Einstein's field equations, discovered in 1963 by Roy Kerr. His solution described a rotating mass warping spacetime, not just inward like a funnel, but also twisting it, dragging the fabric of space and time around the black hole. This discovery fundamentally changed how black holes were understood. Before Kerr, black holes were thought of as simple spheres defined only by mass. After Kerr, black holes became dynamic objects defined by mass and spin. In physics, this spin is called angular momentum, and it dramatically changes the internal structure of the black hole, the behavior of matter near it, and potentially the nature of time itself in its deepest interior regions. Kerr's solution also showed that rotating black holes are more realistic models for what exists in real galaxies, because nearly every observed black hole shows signs of spin, sometimes approaching the theoretical maximum allowed by relativity. The most immediate consequence of rotation is something called frame dragging, a phenomenon predicted by general relativity and studied extensively by physicists including Kip Thorne. Frame dragging means that spacetime itself is forced to rotate around a spinning mass. Near Earth, frame dragging exists but is extremely small. Satellites and precision gyroscopes have measured it, confirming Einstein's predictions. Near a rotating black hole, frame dragging becomes extreme. Instead of spacetime simply curving inward, it also spirals inward like water swirling down a drain. Objects entering this region cannot remain stationary relative to distant space. They are forced to rotate in the direction of the black hole's spin. This twisting of spacetime means that space and time themselves are no longer cleanly separated concepts near a rotating black hole. The geometry of spacetime becomes so distorted that directions that once pointed outward may now point inward, and the difference between motion through space and motion through time begins to blur in ways that challenge intuitive understanding. One of the most important regions created by rotation is called the ergosphere. The ergosphere exists outside the event horizon and forms because space-time is being dragged faster and faster as distance to the black hole decreases. Inside the ergosphere, it is impossible for an object to remain motionless relative to distant stars. Even light is forced to move in the direction of rotation. The boundary of the ergosphere is defined by where frame dragging becomes so strong that stationary motion becomes physically impossible. However, unlike the event horizon, objects inside the ergosphere can still escape if they move fast enough in the right direction. This creates one of the strangest theoretical possibilities in astrophysics. Energy can be extracted from a rotating black hole. Through a process first described by Roger Penrose, particles entering the ergosphere can split into two pieces. One piece falls into the black hole with negative energy relative to infinity, while the other escapes with more energy than the original particle had. This does not violate conservation of energy, because the extra energy comes from the rotational energy of the black hole itself. Over time, this process could theoretically slow the black hole's rotation. While direct Penrose process extraction is difficult to observe, similar effects are believed to power enormous astrophysical jets seen emerging from supermassive black holes at the centers of galaxies. Observations from major space observatories continue to support the idea that many black holes spin rapidly. The NASA and partner agencies use multiple telescopes to study accretion disks, jets, and X-ray emissions around black holes. The Hubble Space Telescope has captured detailed images of jets extending thousands of light-years from galactic centers, indicating extremely energetic processes likely tied to rotation. Meanwhile, the James Webb Space Telescope is providing new data about how black holes formed in the early universe and how quickly they began spinning. By observing early galaxies in infrared wavelengths, Webb can see through cosmic dust and measure how gas falls into early black holes. These observations suggest some black holes began spinning rapidly very early in cosmic history, implying that rotation may play a major role in galaxy formation and evolution. Rotating black holes also contain a more complex internal structure than non-rotating ones. Instead of a single event horizon, rotating black holes mathematically contain two horizons. The outer horizon behaves like the event horizon already described. the point beyond which escape is impossible. But deeper inside exists something called an inner horizon, sometimes called the Cauchy horizon. The existence of this inner horizon creates theoretical possibilities that are deeply strange. According to some mathematical solutions, crossing the inner horizon could lead to regions where time and space swap roles, or where paths through space-time could theoretically loop back toward earlier states. These solutions even allow, mathematically, for pathways that could connect to other universes or distant regions of space-time. Most physicists believe these inner horizon structures would be unstable in reality due to quantum effects and energy buildup, but they remain one of the most fascinating predictions of general relativity. The mathematics suggests that rotating black holes are not simple dead ends, but incredibly complex space-time structures whose true nature may require a complete theory of quantum gravity to understand fully. Another major consequence of rotation is how matter behaves as it falls into a black hole. Accretion disks around rotating black holes can become extremely efficient at converting mass into energy. In some cases, up to 40% of the rest mass energy of infalling matter can be converted into radiation, far more efficient than nuclear fusion in stars. This efficiency helps explain why active galactic nuclei and quasars are among the brightest objects in the universe. As matter spirals inward, magnetic fields twist and stretch, accelerating charged particles to near light speed and launching them into space as jets. These jets can shape entire galaxies by heating surrounding gas and regulating star formation. Observations from X-ray telescopes and radio observatories confirm that jet strength often correlates with black hole spin. Faster spin generally means stronger jets and more energetic output. From a time perspective, rotating black holes introduce even more extreme relativistic effects than non-rotating ones. Time dilation still occurs, but rotation means that observers moving in different directions around the black hole could experience different rates of time flow. Inside the ergosphere, space-time is dragged forward so strongly that all future paths are partially aligned with the direction of rotation. This means that even if an object tries to move opposite the spin, space-time itself carries it forward. From a distant observer's perspective, objects near the horizon appear slowed and redshifted. From the perspective of the falling observer, time still feels normal locally, but the external universe appears to speed up dramatically. In extreme cases near supermassive black holes, an observer falling inward could theoretically witness large portions of the future evolution of the external universe in a very short period of personal time. These effects are not science fiction inventions. They are direct mathematical predictions of relativity under extreme gravitational conditions. Rotating black holes also raise deep questions about causality. In some mathematical solutions, deep inside rotating black holes, space-time paths exist that could theoretically loop back in time. These paths are called closed time-like curves. Most physicists believe real-world quantum effects or instabilities would prevent these loops from forming. But their presence in mathematical solutions suggests something important. General relativity alone may allow violations of simple cause and effect order if pushed to extreme limits. This is another reason why a full theory of quantum gravity is needed. It may explain how the universe preserves causality even under extreme gravitational conditions. Some theoretical models suggest quantum fluctuations near inner horizons would destroy any structure that might allow time loops, effectively protecting the timeline of the universe. Rotating black holes also influence the way gravitational waves are emitted during mergers. When two spinning black holes collide, the gravitational wave signal carries information about spin alignment, spin speed, and orbital dynamics. Detectors on Earth can now measure these details. By analyzing gravitational wave signals, scientists can determine whether black holes formed from isolated stars, from dense star clusters, or from previous black hole mergers. Some observed mergers show evidence of complex spin orientations, suggesting black holes may merge multiple times throughout cosmic history. This helps build a picture of black holes not as isolated endpoints, but as evolving populations shaping galaxy structures over billions of years. From a broader cosmic perspective, rotating black holes are engines of transformation. They shape star formation. They influence galactic structure. They generate jets that can stretch across intergalactic space. They convert gravitational energy into radiation with incredible efficiency. And they provide one of the few places where the most extreme predictions of relativity can be tested. Every new observation from space telescopes, gravitational wave detectors, and radio observatories adds new data to refine these models. The universe continues to reveal that black holes are not just destructive objects, but central players in cosmic evolution. From a calm, sleep-focused perspective, rotating black holes represent motion on cosmic timescales. Their spin can last billions of years. Their effects unfold slowly across galaxies. Matter spirals inward gradually, glowing softly in X-rays and infrared light as it falls. Jets launch across space over millions of years. Time near them stretches, slows, and distorts in ways far beyond everyday experience. They exist as slow, patient engines in the background of the universe, shaping structure over immense spans of time. The study of rotating black holes continues to push physics forward. They connect relativity, quantum theory, thermodynamics, and information theory. They force deeper questions about the nature of time, space, and reality. And they remind science that the universe often behaves in ways that seem impossible at first, but become understandable through mathematics, observation, and patient investigation. The next chapter will move deeper into one of the most debated ideas in theoretical physics, whether black holes could connect to other regions of space-time through wormholes, and whether these structures could ever be stable or traversable under real physical laws. Chapter 6. Wormholes and Bridges Through Space-Time. Could black holes connect universes? The idea that black holes might not simply destroy everything that enters them, but instead might connect distant regions of space or even entirely different universes, emerges directly from the mathematics of general relativity. These theoretical structures are called wormholes, and while they are often associated with science fiction, their origin is rooted in serious physics research. The earliest mathematical description came from solutions to Einstein's field equations studied by Albert Einstein and Nathan Rosen in 1935. Their work described what is now called an Einstein-Rosen bridge, a theoretical tunnel connecting two separate regions of space-time. In its simplest mathematical form, this bridge links two black holes, potentially allowing matter or information to pass from one side to the other. However, early analysis suggested these bridges would collapse instantly, preventing anything from traveling through them. Even so, the possibility that space-time itself might contain shortcuts or tunnels fundamentally changed how physicists thought about the structure of the universe. Instead of space-time being smooth and continuous everywhere, it raised the possibility that extreme gravity might tear or reconnect space-time in complex ways. To understand why wormholes appear in relativity equations, it is helpful to think about space-time as a flexible geometric structure rather than a rigid stage. General relativity describes gravity as curvature, meaning mass and energy bend space-time. Under normal conditions, this curvature is gentle. Around planets and stars, it simply creates orbits. But under extreme conditions, like those inside black holes, space-time curvature becomes extreme enough that it can mathematically fold back on itself. When space-time folds in this way, two distant regions can become directly connected, like 2 points on a folded piece of paper touching, even though they were far apart before folding. In theory, a wormhole could allow travel between these regions much faster than traveling through normal space. However, most wormhole solutions require conditions that may not exist naturally, such as exotic matter with negative energy density. Negative energy is not purely fictional. Quantum physics allows small amounts of negative energy in certain situations, such as the Casimir effect, but whether enough negative energy could exist to stabilize a wormhole remains unknown. The connection between black holes and wormholes becomes more complex when considering rotating black holes. Some mathematical solutions suggest rotating black holes could naturally contain tunnel-like internal structures. These solutions show space-time paths that do not simply end at singularities, but instead continue into other regions. However, these solutions assume perfect symmetry and do not account for quantum effects, radiation, or turbulence in real astrophysical environments. Most modern physicists believe that real wormholes, if they exist, would be extremely unstable. Even small disturbances, like particles or radiation entering the wormhole, could cause it to collapse instantly. This instability remains one of the biggest barriers to wormholes being usable or traversable in any practical sense. Even so, the mathematics continues to be studied because it reveals deeper truths about gravity and spacetime. Wormholes highlight how incomplete current physics is when trying to combine relativity and quantum mechanics. Modern research into wormholes has become deeply connected with quantum information theory. Some physicists now suspect wormholes and quantum entanglement may be related at a fundamental level. Theoretical work suggests that entangled particles may be connected by extremely tiny spacetime bridges at the quantum scale. This idea is sometimes summarized in the phrase ER equals EPR, linking Einstein-Rosen bridges with quantum entanglement described by Einstein, Podolsky, and Rosen. While this idea remains theoretical, it suggests spacetime geometry and quantum information may be deeply connected. If correct, spacetime itself might emerge from quantum relationships between particles. Black holes play a central role in this research because they naturally combine gravity, thermodynamics, and quantum effects. Some theoretical models suggest the interior of a black hole might be describable as a form of quantum information network rather than classical geometry. This would mean wormholes are not simply tunnels through space, but manifestations of quantum information connections. Observational astronomy continues to search for evidence that could indirectly support or rule out wormhole theories. While no telescope has observed a wormhole directly, advanced observatories continue studying black hole behavior in increasing detail. Agencies like NASA coordinate global observation efforts combining multiple wavelengths of light, gravitational wave signals, and radio telescope data. The James Webb Space Telescope is particularly important because it can observe extremely early galaxies, giving insight into how black holes formed and evolved during the first few 100 million years after the Big Bang. If unusual gravitational lensing or energy patterns are ever observed that cannot be explained by normal black hole physics, it might hint at exotic spacetime structures. Meanwhile, gravitational wave observatories continue detecting black hole mergers. If wormholes exist, they might produce unusual gravitational wave signatures that differ from normal black hole collisions. So far, all detected signals match predictions from standard relativity, but observation technology continues improving. Another important question is whether wormholes, if they exist, could allow time travel. Some mathematical wormhole solutions allow paths that loop back in time, called closed time-like curves. However, most physicists believe quantum effects would prevent stable time loops from forming. The universe appears to preserve causality, meaning cause must come before effect. Some theories suggest quantum fluctuations near wormhole throats would destroy any structure that could allow backward time travel. Others suggest unknown quantum gravity effects enforce causality at a fundamental level. Even if time travel were mathematically possible, it might be physically forbidden by deeper laws of nature, not yet discovered. This concept is sometimes called chronology protection, the idea that the universe prevents paradoxes from forming. Wormholes also raise questions about whether the universe is connected in ways not yet visible. Some cosmological theories suggest the early universe may have contained microscopic wormholes formed during rapid expansion after the Big Bang. If any survived, they would likely be incredibly tiny and unstable. Some speculative models suggest advanced civilizations, if they exist, might attempt to stabilize wormholes using exotic matter or advanced technology. However, there is currently no scientific evidence supporting this possibility. The energy required to stabilize even a microscopic wormhole would likely exceed the total energy output of entire stars. This places wormhole engineering far beyond current or foreseeable technology. From a purely scientific perspective, wormholes remain valuable even if they never exist physically. They provide testing grounds for theoretical physics. They help reveal inconsistencies between believable physical laws. They force physicists to confront the limits of relativity and quantum mechanics. They help guide research into quantum gravity, one of the most important unsolved problems in physics. Wormholes are not just about travel or science fiction ideas. They are about understanding how space-time itself is constructed at the deepest levels. The study of wormholes has led to breakthroughs in understanding black hole entropy, quantum entanglement, and the holographic principle. These ideas are now central to modern theoretical physics. From a cosmic perspective, if wormholes exist naturally, they would likely be extremely rare and short-lived. The universe appears stable and protects large-scale structure. Most black holes appear to behave exactly as predicted by standard relativity. No observed black hole shows clear evidence of being a traversable tunnel. Even if wormholes exist, they may only form under extreme conditions for extremely short periods of time. Detecting one would require precise measurements of gravitational distortions, radiation patterns, or gravitational wave signals. Future generations of observatories may eventually be sensitive enough to detect these effects, but currently, wormholes remain theoretical constructs supported by mathematics rather than observation. From a calm, sleep-focused perspective, wormholes represent possibility rather than danger. They exist mostly as mathematical shapes in equations describing spacetime. If they exist physically, they would likely be far from Earth, deep in extreme gravitational regions. The universe continues expanding quietly. Galaxies drift slowly apart. Black holes spin and slowly evolve over billions of years. Even the most extreme cosmic structures operate on timescales far beyond human experience. Wormholes, if real, would be part of that slow cosmic architecture, shaping spacetime quietly and invisibly. The study of wormholes ultimately leads back to a deeper realization. The universe is still not fully understood. The laws discovered so far explain enormous ranges of phenomena, but they do not yet form a complete unified theory. Black holes, wormholes, and quantum gravity sit at the boundary of current knowledge. Each new observation from telescopes, each new gravitational wave detection, and each new mathematical breakthrough moves science slightly closer to understanding how reality is built at its deepest level. The next chapter will move into one of the biggest unresolved questions in physics and cosmology: how black holes form in the early universe, whether primordial black holes could exist, and how black holes may have shaped the large-scale structure of galaxies across cosmic time. Chapter 7. The First Black Holes, Ancient Giants and Primordial Shadows. Black holes are often described as the final stage of massive stars, objects born in supernova explosions after millions or billions of years of stellar evolution. But modern astronomy has revealed something far more mysterious. Some black holes appear to have formed extremely early in the universe, possibly even before the first generation of normal stars fully developed. This discovery has forced scientists to rethink how black holes form, how galaxies grow, and how structure emerged in the early cosmos. The study of early black holes sits at the intersection of cosmology, particle physics, and gravitational theory. Observations over the last 2 decades have shown that some black holes reached millions or even billions of solar masses when the universe was less than 1 billion years old. That timeline is difficult to explain using traditional star collapse models alone. This has led scientists to explore alternative formation pathways, including direct collapse black holes and primordial black holes formed shortly after the Big Bang itself. These possibilities are now major research areas in astrophysics. Early black hole formation research builds directly on modern observations from space telescopes and cosmological surveys. Missions operated by NASA and international partners continue to push observations deeper into cosmic history. The Hubble Space Telescope first helped identify extremely distant quasars, showing that supermassive black holes existed far earlier than expected. Later, the James Webb Space Telescope expanded this research by detecting early galaxies and measuring their structure and star formation. Webb's infrared sensitivity allows observation of galaxies formed only a few 100 million years after the Big Bang. Some of these galaxies appear to contain black holes already millions of times the mass of the Sun. This raises a major question: how did black holes grow so quickly? Standard stellar collapse models struggle to produce black holes that large in such a short time. This suggests either extremely fast growth rates or alternative formation mechanisms that bypass the need for stellar evolution entirely. One possible explanation is the idea of direct collapse black holes. In this model, instead of forming from individual stars, enormous clouds of primordial hydrogen gas collapse directly into black holes without first forming stars. For this to occur, cooling processes inside the gas cloud must be suppressed. Normally, cooling allows gas to fragment into smaller clumps that form stars. But under certain conditions, radiation from nearby galaxies or other early cosmic sources might prevent cooling. If cooling is suppressed, the gas cloud collapses as a single structure. This collapse could produce black holes with masses tens of thousands or even hundreds of thousands of times that of the Sun. These larger starting masses would make it easier to explain how supermassive black holes formed so quickly. Direct collapse remains difficult to confirm observationally, but researchers continue searching for early universe signals consistent with this process. Some candidate objects have been observed, but confirmation requires more precise data. Another possibility is even more exotic: primordial black holes. These hypothetical black holes would not form from stars at all. Instead, they would form directly from density fluctuations in the early universe during the first moments after the Big Bang. During the earliest phases of cosmic expansion, matter was distributed unevenly at tiny scales. In some regions, density may have been high enough to collapse directly into black holes. These primordial black holes could have formed with a wide range of masses, from microscopic sizes to possibly stellar scale or larger. If primordial black holes exist, they could solve multiple cosmic mysteries at once. Some theories suggest they could contribute to dark matter. Others suggest they could act as seeds for supermassive black holes in galaxies. Observational searches continue, focusing on gravitational lensing effects, gravitational wave signals, and unusual radiation signatures that might indicate primordial black hole evaporation. Gravitational wave astronomy has opened a new window into early black hole populations. Observatories detecting space-time ripples from black hole mergers can measure black hole masses and spin rates with high precision. Some detected mergers involve black holes heavier than expected from normal stellar evolution models. This has led to speculation that some merging black holes may have formed through unusual channels, possibly including primordial origins. However, most observations still match predictions from standard stellar collapse. Distinguishing between primordial and stellar origin black holes requires larger datasets and improved sensitivity. As gravitational wave observatories become more advanced, they may eventually detect patterns in black hole populations that reveal their origins. Another major question involves how early black holes influenced galaxy formation. Supermassive black holes are found in nearly every large galaxy today. Their mass often correlates with the mass of the galaxy's central bulge. This suggests galaxies and black holes evolved together. Early black holes may have helped regulate star formation by heating gas and launching jets that prevented gas from collapsing into new stars. This feedback process may help explain why galaxies have the structures they do. If early black holes formed quickly, they may have shaped galaxy formation from the very beginning. Observations from Webb are beginning to reveal galaxies that appear more mature than expected for their age. Some scientists believe early black hole activity may have accelerated galaxy development. Early black hole growth likely involved both gas accretion and mergers. Gas falling into early black holes could grow them rapidly if enough material was available. Early galaxies contained abundant gas compared to modern galaxies. This may have allowed early black holes to grow faster than black holes today. Mergers between early galaxies would also bring black holes together, creating larger black holes over time. Each merger releases enormous energy through gravitational waves and radiation. Over hundreds of millions of years, repeated mergers could build supermassive black holes. Understanding these processes helps explain how the largest black holes formed by the time the universe reached 1 billion years of age. Primordial black holes, if they exist, would provide a unique probe of early universe physics. They could provide evidence about inflation, the rapid expansion phase thought to occur immediately after the Big Bang. The distribution and mass range of primordial black holes would depend on the nature of early density fluctuations. Detecting them would provide information about physics at energy scales far beyond what particle accelerators can test. Some experiments search for evidence of primordial black hole evaporation through high-energy radiation bursts. Others search for gravitational lensing signatures where tiny black holes briefly magnify background stars. So far, no confirmed primordial black hole detection exists, but constraints on their abundance continue improving. Another fascinating possibility is that primordial black holes could cluster or merge over time, creating larger black holes that later become galaxy seeds. If this occurred, some supermassive black holes might have started as primordial objects that grew through cosmic history. This would change how galaxy formation is understood. It would also connect cosmology directly with particle physics and quantum gravity theories. Some theoretical models predict primordial black holes could form in specific mass ranges. Observations continue testing these predictions. Each new dataset narrows possible models or strengthens others. From a broader perspective, early black hole formation is deeply tied to the structure of the universe itself. The first black holes may have influenced how matter clustered into galaxies and galaxy clusters. They may have affected how early stars formed and how heavy elements spread through the cosmos. Black holes are not just endpoints of stellar evolution. They may be fundamental building blocks of cosmic structure. This realization has transformed black hole research from a niche astrophysics field into a central part of cosmology. Future observatories will continue exploring this early cosmic era. New space telescopes, next-generation gravitational wave detectors, and advanced radio observatories will help measure black hole populations across cosmic time. Each new detection helps refine models of black hole formation. Eventually, scientists hope to determine whether early supermassive black holes form through direct collapse, primordial formation, or combinations of multiple processes. The answer will help reveal how structure formed in the universe and how gravity behaves under extreme conditions. From a calm, sleep-focused perspective, early black holes formed when the universe was young, hot, and rapidly changing. Over billions of years, they grew slowly, merging and accreting matter. Today, they sit quietly at galaxy centers, shaping structure on enormous timescales. The processes that formed them unfolded slowly across cosmic history. Even the most violent events, like black hole mergers, occur rarely compared to the vast quiet periods between them. The universe evolves slowly, steadily, across billions of years, with black holes acting as long-term anchors shaping cosmic structure. The next chapter will explore one of the deepest unresolved mysteries connected to black holes, the black hole information paradox, the holographic principle, and how information may be preserved even when matter falls beyond the event horizon. Chapter 8. The Information Paradox. Do black holes erase reality? Black holes challenge physics not only because of gravity, singularities, or warped time, but because they raise one of the deepest questions in all of science. What happens to information when matter falls into a black hole? In everyday life, information is constantly transformed but never destroyed. If a book burns, the information is not erased. It is scattered into smoke molecules, heat, and light. In principle, if every particle were tracked perfectly, the original structure could be reconstructed. This idea is fundamental to quantum mechanics. The laws governing particles and energy are reversible at their deepest level. If a system is known perfectly at one moment, its past and future can be calculated. Black holes appear to violate this principle. When matter crosses the event horizon, all information about its internal structure, composition, and quantum state appears to disappear. If black holes truly destroy information, then quantum mechanics, one of the most successful theories ever developed, would be incomplete. This conflict became known as the black hole information paradox. It remains one of the most important unsolved problems in theoretical physics. The information paradox gained global attention largely through the work of Stephen Hawking, who showed that black holes emit radiation due to quantum effects near the event horizon. Hawking radiation is thermal, meaning it appears random. If a black hole forms from complex matter and then evaporates into random radiation, then information about the original matter appears lost forever. This deeply troubled physicists because it contradicted fundamental quantum theory. Hawking originally believed information was truly destroyed in black holes. Later in his career, he reversed this position, suggesting that information might escape in extremely subtle ways through quantum correlations in Hawking radiation. The debate sparked decades of research across relativity, quantum field theory, and information theory. It forced physicists to rethink assumptions about space, time, and the nature of reality itself. One major step forward came from the work of Gerard 't Hooft and later Leonard Susskind, who proposed that information might not be lost inside black holes at all. Instead, information might be stored on the surface of the event horizon itself. This idea became known as the holographic principle. In a hologram, three-dimensional information is encoded on a two-dimensional surface. The holographic principle suggests something similar might occur in the universe. Information about objects falling into a black hole may be encoded on the event horizon surface, rather than stored inside the volume. If true, this would mean space-time itself may behave like a hologram, where deeper three-dimensional reality emerges from information stored on boundaries. This concept fundamentally changes how space and reality are understood. It suggests space itself may not be fundamental, but may instead emerge from deeper information structures. Further development of these ideas came from theoretical work by Juan Maldacena, who proposed a mathematical framework known as the ADS-CFT correspondence. This theory suggests that gravity in a higher dimensional space can be equivalent to a quantum field theory on a lower dimensional boundary. In simpler terms, it suggests that a universe with gravity could be fully described by a system without gravity living on its boundary. While this model applies to specific theoretical universes rather than our exact universe, it provides powerful mathematical tools. It shows that gravity and space-time geometry might emerge from quantum information interactions. Black holes play a central role in testing these ideas because they concentrate gravitational effects and quantum effects into the same region of space-time. Many physicists now believe that solving the information paradox will require understanding how space-time emerges from quantum information networks. Observational astronomy continues to provide indirect tests of these theories. Space telescopes operated by NASA continue studying black hole environments in increasing detail. The James Webb Space Telescope observes early galaxies and helps measure how black holes grow and interrounding matter. The Hubble Space Telescope has measured star orbits near galactic centers, confirming black hole mass and behavior. While these telescopes cannot observe event horizons directly, they help constrain models of black hole growth and energy output. Future telescopes and gravitational wave detectors may detect subtle signatures of quantum effects near event horizons. These observations may help determine whether information truly escapes black holes or remains trapped in ways not yet understood. Another major idea connected to the information paradox is black hole complementarity. This concept suggests that information might appear to be both outside and inside the black hole depending on the observer. To a distant observer, information may appear stored on the event horizon. To a falling observer, information may appear to pass inside normally. Both descriptions could be correct within their reference frames. This idea preserves quantum information while also preserving relativity. However, later work suggested potential contradictions in this model, leading to further debate. Some physicists propose the firewall hypothesis, suggesting that quantum effects at the event horizon might create extremely energetic particle regions that destroy anything crossing the horizon. This would contradict relativity predictions that crossing the event horizon should feel smooth. The firewall debate remains unresolved and continues to drive theoretical research. The information paradox has also led physicists to reconsider the nature of entropy and temperature in black holes. Black hole entropy is proportional to surface area, not volume. This suggests that fundamental information storage in the universe may depend on surfaces rather than volumes. This idea appears in multiple areas of theoretical physics and may connect gravity, thermodynamics, and quantum mechanics at a deep level. If space-time is emergent from information, then black holes may represent the most efficient information storage objects possible. Some theoretical work suggests the maximum information that can be stored in any region of space is proportional to its surface area, not its volume. This idea has implications far beyond black holes and may shape future theories of cosmology and particle physics. The information paradox is not just about black holes. It is about whether the universe is fundamentally predictable. If information can be destroyed, then the universe may contain true randomness beyond quantum uncertainty. If information is preserved, then reality may be fully deterministic at its deepest level, even if it appears random at larger scales. This philosophical implication is one reason the paradox remains central to theoretical physics. It connects mathematics, physics, philosophy, and cosmology into a single problem. Solving it may require a unified theory combining relativity, quantum mechanics, and possibly new physical principles not yet discovered. From a cosmic perspective, black holes may not destroy reality. They may transform information into forms not yet fully understood. The universe may preserve every event in subtle quantum structures spread across space-time. Hawking radiation may slowly release encoded information over extremely long timescales. Black holes may act as cosmic information processors, transforming matter and energy into radiation and quantum correlations. These ideas remain theoretical, but they are grounded in decades of mathematical research and increasingly sophisticated simulations. From a calm, sleep-focused perspective, the information paradox represents the quiet mystery of the universe. Black holes slowly radiate energy across trillions of years. Information may drift outward slowly, encoded in faint quantum radiation. The universe may preserve every moment, every particle interaction, every photon path, even if hidden beyond current measurement. The cosmos may be far more ordered and structured than it appears, even at its most chaotic extremes. The slow evaporation of black holes across unimaginable timescales represents one of the quietest processes in the universe, a gradual transformation of matter into radiation across cosmic ages. The next chapter will explore the far future of black holes and the universe itself, how black holes evolve across trillions of years, how galaxies fade, and what the ultimate fate of black holes might reveal about the ultimate fate of the cosmos. Chapter 9. The Far Future, when black holes become the last lights in the universe. The universe today is still young by cosmic standards. Stars continue to form. Galaxies still glow with stellar light. gas clouds collapse, ignite, and create new generations of stars. But physics predicts that this will not last forever. The long-term future of the universe is governed by thermodynamics, gravity, and cosmic expansion. Over unimaginable timescales, stars will stop forming, galaxies will fade, and black holes may become the dominant remaining structures. Understanding the long-term future of black holes is not just an exercise in imagination. It is a direct extension of physics already tested by observation and experiment. The laws of thermodynamics, quantum mechanics, and relativity all predict how energy spreads, how matter decays, and how gravity shapes structure across vast timescales. Black holes, because they last so long, become central to predictions about the ultimate fate of cosmic structure. Modern cosmology, supported by observations from space telescopes and cosmic background radiation studies, shows that the universe is expanding, and that expansion is accelerating. Measurements from observatories operated by NASA and international partners show that distant galaxies are moving away faster over time. Observations from the Hubble Space Telescope first helped confirm accelerating expansion by measuring distant supernova brightness. Later measurements refined by the James Webb Space Telescope helped measure early galaxy formation and cosmic structure growth. If current models remain correct, cosmic expansion will continue accelerating. Over billions of years, galaxies outside the local group will move so far away that their light will never reach observers here. Eventually, only the nearest galaxies will remain visible. The rest of the universe will fade beyond observational reach. This expansion does not tear apart atoms or solar systems, but it does isolate galaxies from each other across cosmic time. Over trillions of years, star formation will gradually decline. Galaxies form stars by collapsing gas clouds, but star formation consumes available gas. Eventually, most free gas will be locked into stars, stellar remnants or black holes. New star formation will slow dramatically. The remaining stars will be mostly long-lived red dwarfs, which can burn slowly for trillions of years. Eventually, even these stars will exhaust their fuel. The era of luminous stars will fade. The universe will enter what some cosmologists call the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. During this era, occasional collisions between stellar remnants may produce rare bursts of light, but most of the universe will be dark. Gravity will continue to shape structure slowly, pulling remnants together into clusters and eventually into black holes through mergers. Black holes will continue to grow during this period through mergers and slow accretion of leftover matter. Supermassive black holes at galaxy centers may merge if galaxies collide. These mergers release enormous gravitational wave bursts, ripples in space-time traveling across the universe. These waves carry energy away, allowing black holes to settle into new, larger configurations. Over long timescales, galaxies may collapse into fewer, larger structures dominated by massive black holes at their centers. These black holes may slowly consume remaining stellar remnants that drift close enough to cross their event horizons. But even black holes do not last forever. Hawking radiation predicts that black holes slowly lose mass by emitting quantum radiation. The evaporation timescale for black holes is enormous. A stellar mass black hole may last around 1,067 years. Supermassive black holes may last up to 10,100 years or more. These timescales are almost impossible to visualize. The universe today is about 1.38x 1,010 years old. Black hole evaporation will occur across timescales many orders of magnitude longer than the current age of the universe. During most of this period, black holes will emit extremely weak radiation. As they lose mass, their temperature increases and radiation becomes stronger. In the final stages, evaporation may accelerate dramatically. The last moments of a black hole may release a burst of high-energy radiation before the black hole disappears completely. No black hole evaporation has been observed yet because the universe is too young. But the mathematics predicting evaporation is deeply rooted in quantum field theory and general relativity. As black holes evaporate over extremely long timescales, the universe may gradually transition into a radiation-dominated state again. If proton decay exists, then normal matter will slowly disappear over vast timescales as well. Some particle physics models predict protons may decay over timescales longer than 1034 years. If proton decay occurs, then eventually even stellar remnants would dissolve into radiation and lighter particles. In this scenario, black holes would outlast nearly all other structures. Eventually, even black holes would evaporate, leaving only low-energy radiation and elementary particles drifting through expanding space. This possible future is sometimes called heat death, a state where energy is evenly distributed and no useful work can be extracted. Thermodynamics predicts systems tend toward maximum entropy, meaning energy spreads out and becomes less organized over time. Some alternative cosmological models predict different long-term futures. If dark energy changes over time, cosmic expansion could slow, stop, or reverse. If expansion reversed, gravity could eventually cause a big crunch, collapsing the universe back into a dense state. Current observations suggest expansion is accelerating, making a big crunch unlikely. Another speculative possibility is vacuum decay, where the fundamental structure of space changes suddenly due to quantum effects. If vacuum decay occurs, it could alter physical laws instantly across expanding regions of space. There is currently no evidence suggesting this will happen. Most evidence supports continued expansion and eventual heat death. Black holes may play a role even in these extreme future scenarios. Some speculative theories suggest that new universes could form inside black holes through quantum gravitational processes. These ideas remain purely theoretical. If true, black holes might act as seeds for new expanding regions of spacetime. However, no observational evidence supports this idea. It remains a topic of theoretical research and cosmological speculation. Most current models treat black holes as endpoints rather than beginnings, but theoretical physics remains open to new discoveries. From a long-term cosmic perspective, black holes represent the slowest processes in the universe. They form in violent events like supernovae and mergers, but then evolve extremely slowly. They may remain stable for trillions upon trillions of years. Their evaporation represents one of the longest-lasting energy release processes predicted by physics. Even after stars and galaxies fade, black holes may continue radiating faint energy across unimaginable time spans. Eventually, even these structures will disappear, leaving the universe in a state of extremely low energy density and minimal structure. From a calm, sleep-focused perspective, the future universe is quiet. After the bright eras of stars and galaxies, cosmic structure fades slowly. Black holes radiate gently across trillions of years. The universe expands steadily. Energy spreads out evenly. Nothing catastrophic happens suddenly. Instead, the universe drifts toward stillness across enormous time spans. Even the most energetic cosmic events occur slowly when viewed across cosmic history. The future universe may be cold, dark, and quiet, but it will evolve slowly, following the same physical laws that shape the universe today. The next chapter will close the series by stepping back and looking at what black holes teach about reality itself, how they changed physics, how they forced new theories, and why they remain central to understanding space, time, and existence. Chapter 10. What black holes reveal about reality itself. Black holes began as mathematical curiosities. Today, they sit at the center of modern physics, cosmology, and philosophy. They are not just astrophysical objects. They are testing grounds for the deepest laws of nature. Every major theory describing the universe touches black holes in some way. General relativity predicts their structure. Quantum mechanics predicts their radiation. Thermodynamics describes their entropy. Information theory shapes modern attempts to understand their event horizons. No other known object forces all of these fields to intersect so directly. Over the past century, black holes have transformed from theoretical predictions into observed cosmic structures, confirmed by gravitational wave detectors, high-resolution radio telescopes, and space observatories operated by organizations like NASA. Observations from the Hubble Space Telescope and James Webb Space Telescope continue refining understanding of black hole formation and galaxy evolution. Each new observation reinforces a simple truth: black holes are not rare exceptions. They are fundamental components of how the universe is built. One of the most important lessons black holes teach is that space and time are not fixed backgrounds. Before relativity, space and time were thought of as separate, absolute structures. Einstein's theory changed that by showing that mass and energy shape space-time geometry. Black holes push this idea to its limits. Near black holes, space can stretch dramatically, and time can slow relative to distant observers. These effects are not theoretical guesses. They are measured indirectly through gravitational lensing, orbital measurements, and gravitational wave signals. Black holes demonstrate that time is not universal. It is local. Two observers in different gravitational environments can experience time at different rates. This realization changed physics permanently. It forced scientists to rethink everything from cosmology to satellite navigation. Even GPS satellites must account for relativistic time differences caused by Earth's gravity. Black holes simply represent the extreme limit of these same physical laws. Black holes also teach that information may be the most fundamental ingredient of reality. The black hole information paradox forced physicists to consider whether space-time itself emerges from quantum information. Research inspired by the paradox suggests that geometry, gravity, and possibly even time may arise from underlying information relationships. The holographic principle suggests the universe might store information on boundaries rather than volumes. This idea appears in multiple theoretical models attempting to unify quantum mechanics and gravity. While these theories remain incomplete, they represent some of the most advanced attempts to describe the structure of reality. Black holes forced this research by exposing contradictions between relativity and quantum mechanics. Without black holes, physicists might not have discovered these conflicts as clearly or as early. Another major lesson from black holes is that extreme environments reveal hidden laws of physics. Historically, physics advanced by studying extremes, high speeds, high temperatures, or strong fields. Black holes represent the extreme limit of gravity. By studying them, scientists can test relativity under conditions impossible to recreate on Earth. Each new gravitational wave detection, each new telescope observation, and each new simulation helps test theoretical models. So far, general relativity has passed every test involving black holes. But physicists know relativity is incomplete because it does not incorporate quantum mechanics. Black holes are expected to be where new physics eventually appears. Even small deviations from relativity predictions in future observations could reveal new fundamental laws. Black holes also changed how scientists think about the universe as a whole. Supermassive black holes appear to exist at the center of nearly every large galaxy. Their masses correlate with galaxy structure. This suggests black holes and galaxies evolved together. Black holes may regulate star formation through energy output and jets. They may help shape galaxy size and structure across billions of years. This means black holes are not just endpoints of stellar death. They may be architects of cosmic structure. Understanding black hole growth helps explain how galaxies formed and evolved across cosmic history. Another profound lesson from black holes involves thermodynamics. Black holes obey thermodynamic laws in ways that suggest deep connections between gravity and energy flow. The discovery that black holes have temperature and entropy suggests gravity may be linked to information and statistical physics at a fundamental level. Some physicists suspect gravity itself may emerge from thermodynamic or information principles rather than being a fundamental force. These ideas remain theoretical, but they continue to shape modern physics research. Black holes remain central to testing these theories because they combine gravity, quantum effects, and thermodynamics in a single object. Black holes also teach humility about scientific knowledge. For centuries, humans believed the universe was simple and understandable at all scales. Black holes demonstrate that reality becomes extremely complex under extreme conditions. They reveal that current theories are incomplete. They show that even successful theories like relativity and quantum mechanics may only be approximations of deeper underlying laws. Black holes remind scientists that the universe still holds mysteries beyond current understanding. This drives research forward. Every unanswered question about black holes motivates new experiments, new theories, and new observations. From a philosophical perspective, black holes challenge ideas about determinism, causality, and reality. If information is preserved, then reality may be fundamentally predictable, even if it appears random at large scales. If information can be destroyed, then reality may contain true unpredictability beyond quantum uncertainty. Black holes force scientists to confront these questions directly. They connect physics with philosophy in ways few other objects do. They raise questions about whether time is fundamental or emergent, whether space is continuous or quantized, and whether reality itself is built from information relationships rather than physical substance. From a cosmological perspective, black holes help explain how the universe evolves across time. They influence galaxy formation. They shape star formation. They generate jets that spread energy across intergalactic space. They help regulate matter distribution across cosmic scales. Over extremely long timescales, they may become the last major structures remaining in the universe before slowly evaporating. This makes black holes not just local phenomena, but cosmic-scale players shaping the long-term future of structure and energy distribution. From a calm, sleep-focused perspective, black holes represent slow cosmic processes unfolding across billions and trillions of years. They form in violent events, but then remain stable for enormous spans of time. They spin slowly, they radiate faint energy, they merge rarely. They evolve gradually across cosmic history. The universe itself changes slowly across unimaginable time spans. Black holes represent the deep, slow rhythm of cosmic evolution. Even the most extreme objects in the universe follow physical laws quietly and consistently. The study of black holes continues expanding. New telescopes will observe earlier galaxies. New gravitational wave detectors will detect smaller and more distant mergers. New theoretical models will attempt to unify relativity and quantum mechanics. Black holes will remain central to these efforts. They are not just objects to observe, they are clues to deeper layers of reality. Each discovery reveals something about how space, time, energy, and information interact at the deepest level. In the end, black holes represent the frontier of knowledge. They mark the boundary between what physics currently understands and what remains unknown. They demonstrate that reality is more complex and more beautiful than early science imagined. They show that the universe is not static or simple. It is dynamic, evolving, and full of structures that challenge human intuition. Black holes are reminders that science is a journey. Each discovery answers some questions and reveals new ones. And in that process, the universe slowly reveals how it works, one observation, one equation, and one mystery at a time.